Hello, everyone. I hope you're all safe and sound. Welcome to the 18th lecture on analog and digital electronic circuits, in which we will study the high frequency response of common emitter and common source amplifiers. However, before going into its details, I will discuss a couple of very useful methods which can be used to estimate the higher cutoff frequency of amplifiers. So the magnitude response of an amplifier is given by this curve shown in this diagram here, and is quantified as A of S and is given by the product of these three terms. So this AM here, it represents the midband gain, and it is this constant gain in the midband frequency range, which is independent of the frequency of operation. So in the midband, since we ignore all the capacitive effects, the gain is independent of the frequency and is denoted by AM. On the lower side, in the low band, the gain reduces, it decreases because of the effects of the coupling capacitors. And these effects are taken into account, are quantified by this factor, F subscript capital L of S, which is a function of an n degree polynomial in the numerator and an n degree polynomial in the denominator. So this n degree polynomial has n zeros, which are represented by omega prime z, and n poles, which are represented by omega prime t. So omega prime zk and omega prime tk is the kth real zero and pole frequency in the low band, in this band of frequency of operation. On the higher side, the gain again reduces because of the effects of parasitic capacitors, and this reduction, this profile at the high frequency is modeled by this factor here, which is denoted by F subscript capital H of S. So again, it is an n degree polynomial in the numerator and an n degree polynomial in the denominator, which has n zeros represented by omega z and n poles, which are represented by omega p. So omega zk and omega pk is the kth real zero and pole frequency in the high band. So FLS represents the response of a network which has n poles and n zeros, and it resembles the response of a high pass filter, whereas F subscript H again is a response which is governed by n zeros and n poles, and this response resembles the response of a low pass filter. So this shape, this profile represents the high pass operation, whereas this profile, this curve here, this represents the profile of a low pass filter. At low frequencies, these omega z's and omega p's, they are so large that S over omega z and S over omega p is almost zero, and this F of H is approximately 1. So at low frequencies, the response is given by the product of FL and AM. Similarly, at higher frequency, the omega prime z's and omega prime p's, these zeros and poles, since they are the zeros and poles in the low band, so at high frequencies or at frequencies including the mid band range and the high band range, these zeros and these poles, they are so small that this response FL of S is approximately 1. So at high frequencies, within the mid band and high band, the response is given by AM times F of H, F subscript H of S. So on the lower side, the response is governed by FL. On the higher side, the response is governed by FH. And in the mid band, the pole zero frequencies, omega prime, they are small enough, and the pole zero frequencies, omega, they are large enough that both of these two factors, they are approximately 1. So in the mid band, the response is given by AM. In the lower side, in the low band, the response is given by FL. And in the higher side, in the high band, the response is given by FH. So at frequencies including and beyond midband, FL is approximately 1 for all poles and zeros, because of all the poles and zeros, their frequencies are small enough to be ignored. So FL is approximately 1. And the response, including and beyond midband frequencies, is given by this expression in equation 2. So AH of S represents the response of the amplifier in the midband and in the high frequency range. So in the midband, H of S is approximately 1, and the response is given by AM. And in the high band, the response, the magnitude decreases below AM because F subscript H of S comes into play, and its magnitude becomes less than 1 in the high band. So we call AH of S the high frequency response of the amplifier. And the quantity of interest in the high band, as it was in the low band, is again this 3 dB cutoff frequency, which is in this case now the higher 3 dB cutoff frequency, or also called the higher cutoff frequency. And this is the frequency at which the magnitude of the gain of the amplifier drops below 3 dB, drops by 3 dB below the midband gain, which is equivalent to saying that the gain drops to 70.8% of its midband value. So the frequency at which the magnitude of the gain drops to 70.8% of its midband value, that frequency is called the higher cutoff frequency on the higher side. So the higher cutoff frequency can be found by setting the magnitude of the magnitude response of the amplifier to AM by square root 2, which is 70.8% of AM. But most of the times, solving this equation, solving the magnitude of the response at this value is a mathematically laborious task, which is why we are going to discuss a couple of approximate yet very useful methods which can estimate the higher cutoff frequency of the amplifiers. So the first method is called the dominant pole method, and as the name suggests, it makes use of the fact that there is a dominant pole in the system. So most of the times, the zeros of the amplifier, so this numerator here, which represents n zeros of the amplifier, some of these zeros are already at infinite frequency, and the others, their frequency is so large that within the range of interest, within the frequency range of interest, S over omega zk is almost 1. That is for the kth zero frequency, S over omega zk, where S is the frequency within the range of interest, which is typically close to the midband, because we are interested in the higher cutoff frequency. So higher cutoff frequency lies within the frequency range, which is close to the midband. So in this range of interest, S over omega zk for all k is approximately 1, because the zero frequencies are at such a large value that S over omega zk is approximately 0. So most of the times, typically we will be able to approximate the numerator with 1, numerator of this response FH with 1. On top of that, if we have a dominant pole, that is, if we have a pole frequency which is considerably smaller than all of the other pole frequencies, then the overall response of the amplifier will be governed by that dominant pole frequency. So in this case, I've assumed that omega P1 is the dominant pole frequency. So if omega P1 is the dominant pole frequency, then the higher cutoff frequency will be very well approximated by the dominant pole frequency. So if this FH is very close to FP1, and all the other pole frequencies are at much higher frequency, then within this frequency range of interest, all of these factors, which correspond to the pole frequencies other than the dominant pole, they will be approximately 1, because all of these ratios S over omega p, they will be approximately 0 within this frequency range because of the dominant pole response. So the higher frequency response of the amplifier, it will be determined by the dominant pole, omega p1, which will also estimate the higher cutoff frequency of the amplifier. And as a general rule, we consider a pole frequency as dominant if it is at least 2 octaves away from the nearest pole or zero frequency. That is, if it is at least 2 times smaller than the next pole or zero frequency, then the pole under consideration will be considered as the dominant pole. So if you have a dominant pole, then the response is approximated by this expression, and the higher cutoff frequency is given or estimated, very well estimated, by the dominant pole frequency. Another way to obtain the higher cutoff frequency of an amplifier is to solve FH at the cutoff frequency by setting its magnitude square equal to 0.5. So at cutoff frequency, the magnitude of the gain of the amplifier drops to 70.8% of the magnitude of the gain of the amplifier in the midband. In other words, the magnitude square of the gain of the amplifier drops to 50% of the magnitude square of the midband gain of the amplifier. So this means that at the cutoff frequency, the magnitude square of FH must be 0.5. So we can solve this relation, this equation, and by doing so, we can estimate the higher cutoff frequency of the amplifier. So to elaborate further, let us solve a two-pole 2-0 system for mathematical convenience. So FH is now given by the product of these two factors, which represent the 2 zeros of the system, and the product of these two factors, which represent the 2 poles of the system. So the magnitude square of FH is equal to the magnitude square of the 2 terms in the numerator and divided by the magnitude square of the 2 terms in the denominator. So FH is actually the value of S at omega is equal to omega H. So the magnitude of, for example, this factor is 1 plus omega H square over omega Z1 square square root. So magnitude square will give us 1 plus omega H square over omega Z1 square. Similarly, we can obtain the magnitude square of the other 3 terms, and we'll get a 4th degree polynomial in the numerator and a 4th degree polynomial in the denominator, like this. So under the assumption that this term is really small, because strictly speaking, omega H is less than all the poles and zero frequency. So omega H over omega ZK or omega H over omega PK, it will be less than 1 for all k. This means that omega H raised to the power 4 over omega Z1 square, omega Z2 square, as well as omega H raised to the power 4 over omega P1 square, omega P2 square. Both of these terms, they will be much smaller than 1. So under the approximation that these terms are really small, we can ignore them, and we'll be left with an approximate expression, which is a polynomial of degree 2 in the numerator and a polynomial of degree 2 in the denominator. So simplifying this expression, we can estimate the higher cutoff frequency of the amplifier by this expression. So it is given by all of the pole frequencies and all of the zero frequencies. Since there are 2 poles and 2 zeros, so it is given in terms of the 2 pole frequencies and the 2 zero frequencies. So we can extend this idea to a system with arbitrary number of poles and zeros. And for such a system, the higher cutoff frequency will be given in terms of all the pole frequencies and all the zero frequencies through this expression. So if we look at this expression, then under the assumption that omega P1 is the dominant pole, 1 over omega P1 will be greater than all of the terms inside the square root, because omega P1 will be smaller than all of the pole and zero frequency. So 1 over omega p1 will be greater than all of the terms within the square root, and so the argument within the square root, it can be approximated under this assumption with 1 over omega p1 square, which will estimate omega h to be equal to omega p1 as given in 4. So under the approximation that omega p1 is the dominant pole, this estimate reduces to the estimate given in 4, which approximates omega h with omega p1. The third method approximates or estimates the higher cutoff frequency through the use of open circuit time constants. So please note that FH, which is the product of n factors in the numerator and n factors in the denominator, it can be written as an n degree polynomial in the numerator and an n degree polynomial in the denominator, which is obtained. So the n degree polynomial in the numerator is obtained by multiplying all the n factors in the numerator, and this n degree polynomial is obtained by multiplying all the n factors in the denominator. So these coefficients AKs, they are given by the zeros of the system, because they are obtained by multiplying the n factors corresponding to the zeros of the system. Similarly, the coefficients dk in the denominator, they are given by the n poles of the system. So in particular, this coefficient b1, which is the coefficient of s, this is given by the inverse, the sum of the inverse of all omega p k's. So if we go back to the formulation of FH, then if we multiply all of these terms, all of these factors, then the coefficient of S will be 1 over omega p1 plus 1 over omega p2 plus 1 over omega p3 and so on. So b1, which is the coefficient of S, is given by the sum of the inverse of the angular pole frequency. Furthermore, it can be shown that b1 is exactly given by this expression, where this term RCk times Ck is called an open circuit time constant associated with the capacitor Ck. So this term Ck, RCk is obtained by open circuiting all the other capacitors while considering Ck, and then finding the resistance seen by the capacitor Ck, which is denoted by RCk. So the product of that resistance times the value of the capacitance is called as the open circuit time constant. So since there are n poles and n zeros, there must be n capacitors in the network. So we compute the open circuit time constants for all the capacitors in the network, considering one at a time while open circuiting all the others, and then finding the resistance seen by the capacitor under consideration at V sig equal to 0. After finding all the open circuit time constants, we add them all up, and this gives us V1. So from this information, again, under the assumption that there is a dominant pole in the system, so assuming that omega p1 is the dominant pole, we can approximate b1 as 1 over omega p1. Because omega p1 is much smaller than all the other omega k's, its inverse will be much larger than all the other 1 over omega pk's. So b1 is very well approximated under this assumption by 1 over omega p1. And from the dominant pole method, we know that omega h under this assumption is approximated by omega p1. So in this case, omega h is approximated by 1 over b1, because omega p1 is 1 over b1. So using this method, we can estimate the higher cutoff frequency of the amplifier by the inverse of the sum of all of the open circuit time constants due to all the capacitors in the network. Now that we know different methods to estimate the higher cutoff frequency of an amplifier, we will move towards the high frequency analysis of the common emitter and common source amplifiers. Since their circuits are very similar, I have drawn this general circuit, which represents both common emitter and common source configurations. So this dotted line only means that either BJT or MOSFET is inserted into this network. So if BJT is inserted into this network, then it is biased by RE in the emitter branch, RC in the collector branch, and it is powered by VCC, and it is bypassed by the capacitor CE. If an NMOS is inserted into this network, then it is biased by RS in the source branch, RD in the drain branch, it is powered by VDD, and it is bypassed by the capacitor CS. In either case, the amplifier is AC coupled by using the capacitors C in and C out. The load resistance is denoted by RL, and V-sig is the small signal having internal resistance R-sig. So this general circuit, it represents both the common emitter as well as common source amplifier configuration. So this diagram shows the small signal AC equivalent circuit for the fully bypassed common emitter or common source amplifier, in which these parameters IX, VX, RX, C1, CXY, VY, C2, IY, and RY, they in turn depend on whether this circuit represents a common emitter or a common source amplifier. So if this is a common emitter amplifier, then this becomes the base terminal, this is the emitter terminal, and this is the collector terminal. So IX is the base current, Vx is the base emitter voltage, which is conventionally represented by V pi. Rx is the resistance R pi. C1 is the capacitance between base and emitter, so it is represented by C pi. Cxy is the capacitance between base and collector, so it is C mu. Vy is the voltage between collector and emitter, so it is VCE. C2 is the capacitance between collector and ground, so it can be the collector to substrate capacitance. If there is no collector to substrate capacitance, then C2 is 0. And there is no capacitor here for common emitter amplifier. And Ry represents the AC collector resistance RC. On the other hand, if this represents a common source amplifier, then this is the gate node, this is the emitter, this is the source node, and this is the drain node. So Ix is Ig, Vx is Vgs, Rx is infinity, because there is no resistance between gate and source in the midband. C1 is the gate to source capacitance CGS, Cxy is the gate to drain capacitance CGD, Vy is the drain to source voltage VDS, C2 is the drain to body capacitance CDB, and Ry is the AC drain resistance RD. So here we've assumed that source and body, they are connected to each other, so there is no source to body capacitance. So using this general small signal AC equivalent circuit, we can analyze both common emitter and common source amplifiers simultaneously in terms of these parameters Vx, Ix, Rx, C1, C2, Cxy, Iy, Ry, and Vy. So before proceeding, we noticed that this portion of the network, that is this signal R-sig, this resistance, and this resistance Rx, we can take this portion of the network, we can separate this part of the network from the rest of the circuit, and we can find a simplified Thevenin equivalent circuit for this network. So combining this resistance with this, because these two resistances, they are in parallel, so combining this resistance with this resistance, I have isolated the input side of the small signal AC equivalent circuit to find its Thevenin resistance and Thevenin voltage. So Thevenin resistance is the resistance seen between these two terminals when V-sig is 0. So it is clearly the parallel combination of this resistance and R-sig. On the other hand, V Thevenin is the open circuit voltage between this node and ground. So this voltage between this node and ground is given by the voltage division of V-sig into this resistance and this resistance. So it is given by this ratio. So we can replace this portion of the small signal AC equivalent circuit by this simplified Thevenin equivalent circuit, in which V Thevenin is given by this expression and R Thevenin is given by this expression. So replacing this portion with its Thevenin equivalent circuit, we get a simplified small signal AC equivalent circuit, which is given in this diagram here. So we have V7N, which is given by Vsig, and the other resistances on the input side. We have R7N, which is given by the resistances on the input side. And then we have the capacitances, the dependent source. Furthermore, I have combined all of the resistances at the output node. So R0 is in parallel with RY, which is in parallel with RL. So I have combined all of these three resistances into RL prime. So RL prime is the parallel combination of R0, RY, and RL. So this simplifies the small signal AC equivalent circuit considerably. So in this simplified circuit, we see that CXY is the bridging capacitance between this node, the voltage at which is VI, and between this output node, the voltage at which is VL. So through the use of Miller's theorem, we can decompose, we can break down this capacitance CXY into a capacitor CX on the input side, which is in parallel with, which will be in parallel with C1, and a capacitor CY on the output side, which will be in parallel with C2. And their values will be given by these expressions, in which K is the voltage gain of this circuit in going from this node to this node. So K is VLS over Vx of F. So since we do not know the value of K, we cannot decompose this capacitor CXY into these two capacitances. On the other hand, if we wish to find the value of K by simplifying this circuit, by decomposing this capacitor into CX and CY, then CY is unknown. So CY depends on K. And in turn, if we break this capacitor into two capacitances to find the gain, then CY is unknown. It in turn depends on the gain. So gain is unknown. And if we try to apply Miller's theorem to simplify the circuit to find the gain, then the resulting capacitor on the output side, CY, which in turn depends on the gain, will not be known. So in order to get out of this situation, we use an iterative method in which the voltage gain of the circuit is first obtained in the mid-band frequency range, that is excluding the effects of all the capacitors. So ignoring all the capacitors, we find the voltage gain VL over VI. And then using that voltage gain, we plug the capacitors back in and we break the capacitance, this bridging capacitance, into CX and CY using these expressions from Miller's theorem. So once we have that simplified circuit with CX on the input side, CY on the output side, we find the gain again. That is, we find the ratio VL over VI again using the capacitor CX in parallel with C1 and the capacitor CY in parallel with C2. So that gives us an updated value of the gain, K. And then using that updated value of the gain, we can find the CX and the value of the capacitances, CX and CY again. So we can keep on repeating this procedure until the values for the gain and the capacitors, CX and CY, they converge. However, this involved analysis is no simpler than an exact analysis of the circuit, which is why we rarely follow this method. So instead, what we do is we apply what is called as the Miller's approximation. So in Miller's approximation, we compute the mid-band frequency gain, and then which is given by this expression. And then we use this gain to find the to apply the Miller's theorem to break the bridging capacitance CXY into two capacitors, CX on the input side and CY on the output side, like this. So in other words, we just use the first iteration of this iterative method, and we obtain approximate results. So this is called Miller's approximation, and using Miller's approximation, you can see that the bridging capacitance CXY, which is now divided, which is now broken down into CX and CY, it results in a much simple circuit. It is a very simple circuit. In fact, it is it breaks the circuit down into two STC networks. So this equivalent capacitor combined with this resistance forms an STC network on the input side, And this equivalent capacitance, which is C2 plus Cy, combined with this resistance, it makes another STC network on the output side. So the values of Cx and Cy are obtained from the Miller's theorem, in which the gain K, which is the midband gain, is given by this expression. So you can verify this expression from this circuit. So in the midband, when we ignore C1, Cx, Y, and C2, then there is an open circuit here, and VL is given by minus GM Vx times RL prime. So VL over Vx will be minus, and since Vx is equal to Vi, so VL over Vi will be minus GM times RL prime. So using this value of K, we can apply Miller's theorem to get this approximate circuit, which is a combination of two STC networks, one on the input side, one on the output side. So we will get two poles. One will be governed by the parameters on the input side, and the other pole frequency will be governed by the parameters on the output side. So using the simplified approximate circuit, we can find the response, which is the ratio of VL to V Thevenin, and this is given by the ratio of VL to Vi times Vi to V Thevenin. So Vi is equal to Vx, and VL to Vx is given by this side of the network, so minus GM Vx times this equivalent impedance gives us VL. So VL over Vx is minus GM times this equivalent impedance. So this equivalent impedance is RL prime in parallel with the capacitive reactance of C2 plus Cy. Similarly, Vx over V Thevenin is given by the division of V Thevenin into R Thevenin and this equivalent reactance. So this equivalent capacitive reactance is the capacitive reactance of C1 plus Cx. So the capacitive reactance of C1 plus Cx divided by that reactance plus R Thevenin gives us Vx over V Thevenin. So by opening up this parallel combination and simplifying, you will be very easily able to see that the resulting expression can be written in this form as a product of these three factors, where this is the midband gain of the amplifier, and these are the two. This is the response of the output STC network, and this is the response of the input STC network, in which omega P naught, which is the pole frequency due to the output STC network, is given by the equivalent capacitance times RL prime. Similarly, omega P1 is given by the equivalent capacitance on the input side times R Thevenin. So if you look closely, then these are nothing but open circuit time constants. So if I open circuit this equivalent capacitor and short circuit V sig to 0, since V sig equal to 0 means V Thevenin will be 0, then the equivalent capacitance seen by this equivalent capacitor will be R Thevenin. So we have P1 plus Cx times R Thevenin. This is the open circuit time constant due to the input loop. On the other hand, if V sig is set to 0, which will set V Thevenin to 0, then Vx will be 0, which means that this will be open circuited. So the equivalent resistance seen by this equivalent capacitance will be equal to RL prime. So this equivalent capacitance times RL prime is the open circuit time constant due to the output loop. So their inverse gives us the respective pole frequency. So Px, like I said, is Px and Cy, they are both given by the Miller's theorem, in which K is equal to minus Gm times RL prime. And since for fully bypassed common emitter or common source amplifier, K is typically much larger than 1, this would mean that Cx will be much greater than Cy. So Cx will be much greater than Cy. Also, if R Thevenin is much greater than RL prime, then this product will be much greater than this product, which would mean that omega Pi will be much smaller than omega P naught. So omega Pi, or in other words, FPI, will be rendered as the dominant pole frequency. So if this is the case, then the higher cutoff frequency can be approximated by the dominant pole frequency. So looking at this transfer function, we see that there are no finite zero frequencies. All the Since there are two poles, there must be two zeros because the number of poles in a system must equal the number of zeros in the system. So because there are no finite zero frequencies, we conclude that both of the zero frequencies they are at infinite frequency. So both of the zeros they are at infinite frequencies, which means that FH will be given only by the sum of the inverse of the square of the pole frequency. So which can be written like this. So if FPI is the dominant pole, then FPI over FP0 will be smaller than 1, and its square will be even smaller than 1, which means that the denominator will be approximately 1. So FH will be estimated by the dominant pole frequency, FPI, which from this expression is given by 1 over 2 pi times the equivalent capacitance on the input side times the Thevenin resistance. We can furthermore estimate the higher cutoff frequency of this circuit by the use of open circuit time constants. So since there are 3 capacitors in this network, there will be 3 open circuit time constants, one due to C1, the other one due to CXY, and the third one due to C2. So considering C1 while open circuiting CXY and C2, we see that at Vc equal to 0, V7N is 0, and the resistance seen by C1 will be R7N. Between this node and ground will be R7N. Similarly, considering C2 while open circuiting CXY and C1, when we short circuit V6 to 0, V7N will be 0, which will mean that Vi or Vx will be 0, which will mean that this will be an open circuit. Hence, the resistance seen by the capacitor C2 between these two nodes will be equal to RL prime. So RC1 is R7 and RC2 is RL prime. On the other hand, the capacitance, the resistance seen by the capacitor CXY can be found by open circuiting C1 and C2, and then applying a current source here and finding its voltage. So the ratio of this voltage to current will give us the resistance between this node and this node. That is between the nodes of the capacitance CXY at Vc equal to 0. So open circuit time constants are found at Vc equal to 0. So this resistance is found at Vc equal to 0. So when Vc is 0, V7N is 0. So V7N is shorted to ground. We're left with R7N. There are no C1, C2. And we remove CXY and put a source in between the terminals to find the ratio of the voltage to the source current. So we note that Vx is given by minus. So Ixy flows from left to right, and minus Ixy flows from right to left through R7N. So minus Ixy times R7N is equal to the voltage at this node with respect to ground, which is Vx. Similarly, Vy is Ixy minus GMVx. So Ixy minus GMVx is the current going through RL prime. So that current times RL prime gives us the voltage at this node. So we put the value of Vx in here, and this is what we get. So the resistance seen by the capacitor CXY is given by Vyx, which is the voltage at this node with respect to this node, divided by Ixy. So Vyx is given by Vy minus Vx. So putting these two expressions in here and simplifying, we get the resistance seen by the capacitor CXY to be given by this expression. That is, it is given by R7N, GM, and RL prime. So knowing these 3 open circuit time constants, we can add them all up, take the inverse, and divide by 2 pi to estimate the higher cutoff frequency of this circuit by this expression. So unlike before, where the higher cutoff frequency was given by C1, Cx, and R7N, in this case, the higher cutoff frequency is given by C1, R7N, C2, RL prime, and GM, in addition to Cx and Cy, which are the contributions due to CXY. Finally, we can carry out an exact analysis of this amplifier configuration by finding out an exact transfer function, that is an exact ratio of VL to V7N. So we do that by finding a ratio of VL to VI, and then we find the ratio of VI to V7N. So if we write KCL at this output node, then there are 4 branches connected to this output node. This one, this, and this. So the current flowing from left to right through CXY is given by the sum of GM plus the current through C2 and the current through RL prime. So the current through CXY from this node towards this node is given by SCXY times the voltage of this node with respect to this node. So the voltage at this node is VI with respect to ground, voltage at this node is VL with respect to ground. So voltage of this node with respect to this node is VI minus VL. So SCXY VI minus VL gives the current flowing through CXY from left to right, from this node to this node. This current is equal to GMVI because Vx is equal to Vi, plus the current through C2, which is given by SC2 times the voltage across C2, which is VL, Vy is equal to VL, plus the current through RL prime, which is VL over RL prime. So we collect the terms corresponding to Vi on the left side and collect the corresponding terms, the terms which correspond to VL on the right hand side. We simplify by taking the LCM, and then we take Vi out common from this side and divide on this side, on the right side. We get this expression, in which we can take this term minus GM RL prime from the denominator out common, and will be left with this expression. So Vi in terms of VL or VL in terms of Vi is given by this expression. Now we can write Vi in terms of VThevenin. So VThevenin is divided between RThevenin and Vi. So VThevenin is the voltage drop across RThevenin plus Vi. Voltage drop across RThevenin is the current through RThevenin times RThevenin. So the current through RThevenin, which flows from this node to this node, that is from left to right, is the sum of the currents through C1 and CXY. So the current through C1 is given by SC1 times the voltage across C1, which is Vi, plus the current through CXY. We have already obtained it as CXY, SCXY times Vi minus VL. So this current multiplied by RThevenin plus Vi gives us VThevenin. So we can simplify, take the terms corresponding to Vi, collect them together, separate out the VL term, and put Vi from this expression in here. Take the LCM, take the denominator onto the other side, take VL out common, simplify, and then take the ratio of VL to VThevenin, which will be equal to this factor divided by this factor in the denominator. So this factor in the parentheses, sorry. So this factor, VL over VThevenin, will be equal to this factor divided by this factor in the parentheses. So this factor in the parentheses can be obtained by analyzing this expression. So if I take the LCM, so first of all, I multiply these two factors. So I get 1 plus S times C1 plus CXY RThevenin plus S times C2 plus CXY RL prime plus the product of these two terms, which is S square times C2 plus CXY times C1 plus CXY times RThevenin times RL prime. And then since I have taken minus GM RL prime times this term out common on the other side, so this will become plus, and it will be multiplied by GM RL times this term. So we'll have S CXY RThevenin GM RL times the first term, GM RL prime times this first term. VL is taken out common, and then this term will be multiplied by this term. So we'll get minus, because this is a plus because I've taken minus out common on the other side. So minus S square times C square XY times RThevenin times RL prime, because G and GM will get cancelled out. So this is the fourth term. In all of these terms, I've taken VL out common. So VL over VThevenin is this factor divided by this factor. So we can see that the denominator is a second ADE polynomial. So this means that there are two poles, as we have established earlier as well. So I can, denoting by ds the denominator, I can factorize this polynomial and write it as a product of these two terms, which when I open up gives me this polynomial. So this this term, which is the coefficient of S, must be equal to this term, which is the coefficient of S. Similarly, this term, which is the coefficient of S squared, must be equal to this term, which is the coefficient of S squared. So I equate these two terms to the corresponding coefficients, and I get these relations. So again, under the assumption that omega p1 is the dominant pole, I can write the inverse of omega p1 and plus the inverse of omega p2 as approximately the inverse of omega p1, because 1 over omega p1 will be much larger than 1 over omega p2 under this assumption, which means that omega p1 will be approximated by the inverse of this factor. And this will give us a very good estimate of the higher cutoff frequency of the amplifier. So using this expression, I can find omega p2. So omega p2 is 1 over omega p1 times 1 over this factor. So 1 over omega p1 is this factor, which is the numerator here, times 1 over this factor, which comes in the denominator here. So under this assumption, we find the two pole frequencies given by these expressions, in which omega p1 very well approximates the higher cutoff frequency of the amplifier. On the other hand, we see that the numerator is a polynomial of degree 1, which means that there is 1 0 at finite frequency. But since there are two poles, there must be two zeros. So the other 0 is at infinite frequency. So this 0 at finite frequency is given by gm over cxy, because if I put s equal to gm over cxy, this factor will become 1 and this numerator will become 0. So the transfer function will become 0. So the finite frequency 0 is given by gm over cxy. And like I said, the other 0 is at infinity. And you can verify it from this overall transfer function in 26. That if I assume s to be infinity, then I can divide in the numerator as well as in the denominator each term by s. So when I divide this term by s, it will become 1 over s, which at s is equal to infinity will become 0, and this term will become independent of s. So in the numerator, I'll have, since gm will get cancelled out in the numerator at s is equal to infinity, I'll have minus RL prime cxy. Similarly, in the denominator, when I divide the first term by s, it will become 0 at s is equal to infinity. When I divide this term by s, s will get cancelled out and I'll be left with this constant. And when I divide this term by s, I'll get an s here with this coefficient. So the numerator will be constant, denominator will be constant plus s times this factor. So at s is equal to infinity, numerator will be finite, constant, and denominator will be infinite. So VL over V Thevenin will be infinity. So as s approaches infinity, in other words, as the frequency increases towards infinity, towards very large values, this transfer function, it approaches 0. So this implies that the other 0 must be at infinity. So there is a 0 here at this frequency and the other 0 is at infinity. And since typically this capacitance, bridging capacitance, is much smaller than GM, the corresponding 0 frequency is very large, and hence it has a negligible effect on the cutoff frequency, which justifies our assumption of dominant pole, because the corresponding 0 frequency is typically large enough to have almost no effect on the higher cutoff frequency of the amplifier. So in which case, there is a plausible reason to assume that one of the two poles is a dominant pole. So we have found this frequency for the 0 by finding the overall transfer function, but we can avoid by analyzing this circuit directly. So we can avoid this whole mathematical derivation and analyze this circuit directly to find the frequency of the zero. So we analyze this circuit because at zero, the transfer function goes to zero. So we assume that, and since the transfer function is the ratio of VL to V7N, so we analyze this circuit at VL is equal to zero. So instead of doing all of this mathematics, we simply analyze this circuit at VL is equal to zero. And VL will be zero only when the current through this equivalent impedance is zero. In other words, the current through CXY is equal to GMVX. So the current through CXY is SCXY times VI minus VL. VL has been assumed to be zero. So it is SCXY times VI minus zero. And the current through this source is GMVX, which is equal to GMVI. So this quick analysis directly gives us the frequency of the zero. So when VL is zero at that frequency, we replace S with SV because we have a zero at that frequency. So SV CXY VI minus zero is the current flowing through the capacitor CXY from left to right. And if it is equal to GMVI, then the current flowing through the output equivalent impedance is zero, which means that VL is zero. So solving this equation directly gives us the frequency of the zero. So instead of solving the whole overall transfer function of the amplifier, if one is interested only in the zero frequencies, then this is a quick method to find the frequency of the zero of the system. Moreover, if we compare 17 and 26, so 17 is the transfer function obtained using Miller's approximation. So in 17, we see that the transfer function we obtain has both of the zero frequencies at infinite value. So both of the zeros are at, in this transfer function, both of the zeros are at infinite frequency. Whereas the exact transfer function we obtained here in 26 shows that one of the zeros is at finite frequency. So this is a typical artifact of applying Miller's theorem, that whenever we apply, Miller's approximation. So whenever we apply Miller's approximation, a zero of the transfer function may get eliminated, like it does in this case, because from using the Miller's approximation, the transfer function we obtained, it shows that both of the zeros they are at infinity. But in actual exact expression, we see that one of the zeros is still at finite frequency. So whenever we use Miller's approximation, one should keep in mind that it may eliminate one or more of the zeros of the circuit, of the transfer function of the circuit. Finally, we analyze the circuit under the assumption that R sig is small. So this is very commonly found scenario. This is a very commonly found case because typically the internal resistance of a signal generator is very small, of the order of 50 ohms. So if R sig is very small, then R7N is very small. So in the limiting sense, we can take both to be equal to zero. And then if we take R7N to be equal to zero, because we have taken R sig to be equal to zero, then the transfer function in 26 is given by this approximation. So we can go back and see that if we put R7N equal to zero, so if we put R7N equal to zero, so this term goes to zero, so we'll be left with this term, and then this term will be zero. So we'll be left with denominator, we'll be left with the same numerator, and then 1 plus S times this second term. So this is what we get. So in this approximate expression, we see that the midband gain of the amplifier remains the same. The zero frequency of the amplifier remains the same. However, the pole frequencies, they have changed. One of the poles has now been shifted to infinite frequency. So the pole due to C1 and R7N, it has been shifted to infinite frequency. And we are only left with one other finite pole frequency, which is given by 1 over 2 pi times C2 plus CXY times RL prime. So since there is only one pole frequency, this must be the cutoff frequency of the amplifier. So under this assumption that R sig is very, very small, the cutoff frequency of the circuit is given by this expression. So it is determined by the open circuit time constant. So it is determined by the capacitance C2 on the output side and RL prime. So referring to figure 6. So see in this figure, you can see that if R7N is almost 0, then the cutoff frequency, the pole frequency associated with this time constant becomes infinity. And we are only left with the pole frequency due to the output loop of the amplifier. So we get the pole frequency, which is a function of C2, RL prime, and CXY. Since we have analyzed this circuit without the use of Miller's approximation, instead of getting CY, we get the output pole frequency in terms of C2, RL prime, and CXY. So instead of getting CY, we have CXY because we haven't used the Miller's approximation. So in all of this analysis, we have assumed the transfer function to be given by the ratio of VL to V7, whereas the actual transfer function is actually VL over V6. But please note that the profile of VL over V7 is exactly the same as VL over V6, because VL over V6 is given by VL over V7 times V7 over V6. And V7 over V6 from equation 14 can be seen to be given by this resistive ratio. So this is just a scalar. So V7 over V6 is just a scalar. So this is just a scalar. So a scalar does not change the profile of the transfer function. So the poles and zeros of the transfer function, of this transfer function, they will be the same as the poles and zeros of this transfer function. Only the constant midband gain, AM, will be changed, will get changed, because this is a scalar. So that is why we were able to analyze VL over V7 instead of VL over V6, because VL over V6 is just given by a scalar times VL over V7. So it is just a scaled version of VL over V7. So the poles and zeros of VL over V7, the poles and zeros of VL over V6, they are the same in all of this analysis as the poles and zeros of VL over V7. So this brings us to the end of this lecture. Thank you very much for your time, and I will see you in the next class. Take care.